First of all, let me thank Vivek for arranging this webinar. Uh, Basically, the whole idea when he approached me was that we have a lot of these new developments and applications in civil engineering for different computers and programs and artificial intelligence and Internet of Things and so on. So coming from industry, I thought that I would share some of the technologies with our fellow civil engineers in Nagpur, and let us see if this can help you in either academics in terms of taking up new projects or getting into new areas, or uh, looking at different type of job markets and so on. So that's the basic idea, and I want to also initially say that this is going to be a presentation which is more of introduction to different technologies. So I wouldn't go more into the technical details or mathematical details. So I don't want to scare anybody that we will be looking at very involved modeling or anything like that. So this is more of a introduction, but only for a little bit of knowledge-based expert systems and artificial intelligence, this neural networks. These are the two areas where I will take one example and we will go little more details into it. So let me thank management, head of the department, and all the organizers at Ramdev Baba College of Engineering and Management, Nagpur, for having me this opportunity to talk to you. Let us look at the agenda for today. I will just introduce myself a little bit, and then we will see what is driving the change in civil engineering, and why so much of computerization or architecture, artificial intelligence, knowledge-based systems, Internet of Things, various type of new technologies are coming up in civil engineering. What is the reason behind it? And the whole thing is, as you will notice, is because of the urbanization, and this large-scale urbanization is what is impacting the AEC industry, and that's why we are required to look at smart cities, to everything related to the computer applications in civil engineering. We will talk also about latest trends in AEC industry, and then we will go into little bit of history of how the computing has started in civil engineering, and go up to the artificial intelligence, Internet of Things, and generative design and latest things. Little bit of details on expert systems and artificial neural network applications in AEC. And depending on what is the time remaining with me, we would go into as much details for generative design, Internet of Things, AR, VR. Basically, it's more applications related to the reality and augmenting the virtual with the real life situations. And then to conclude, I will briefly mention about the BIM 3D, 4D, 5D, 6D, and so on, 3D printing, and then we will go for the question and answers. So just something about me. I'm from Nagpur, and out of Nagpur since 85 after 12th standard, but out of India since 95. And last 22 years, I'm in Dubai, working for a company that is involved in computer-aided engineering. So basically, I have not left my domain area, and we are developing different offerings to market based on the application of computers in civil engineering. I did my graduation from Walchand College of Engineering, then did my MS in structures from Maharaja Sayajirao University of Baroda, and PhD in application of artificial neural networks in structural engineering from IIT Bombay in 1995. Ever since, I hardly worked in India basically. And just because today we are talking in academic, so I thought, like, I will, in fact, I actually had to find out how many publications I have. So I have published a lot of papers in computers, not a lot of, it's only 25. A lot of good journals like American Society of Civil Engineers, Structural Engineering, Computers and Structures, and so on. And I've been to committee meetings also for AEC in California. Before this presentation, I have done a couple of presentations in Nagpur, and I don't really remember that, but I feel I have been to your college as well. There was a ADCC in Nagpur. There I have done some presentations, and also at a seminar of Institution of Engineers. And working experience is like I have been working mostly in Dubai for last 22 years. Before that, I have worked in Kuwait and in Henniker in Boston. Actually, it's basically for the company called Softdisk and Autodesk. We had some assignments over there. So that's briefly about me. Let us see now how the urbanization is impacting the AEC industry. Now, this graph, this is United Nations urbanization prediction. So, as you can see that in the year 2009, the number of people living in urban area are actually crossing over than the number of people living in rural areas worldwide. Now, what that has to do with AEC? So basically, if you will see the impact of this on the AEC, you will find that everything related to the problems of people or problems of population are basically related to water supply, electricity supply, health centers, building factories and skill development, cost-effective housing projects, mass production, prefabrication. You will see that whatever the issues of urbanization, that those issues are directly impacting the AEC industry. I mean, in Nagpur, I believe you have something called multi-mode hub, transport hub. It's called Mihan, I think, and that is basically to merge the road traffic, railway traffic, air traffic, and all these things for creating the transportation hub. If you look at any city, the most probably you will find a metro project. You will find that there are roads and bridges being built everywhere, linking of rivers. And recently, if you see the news, what you are seeing is also the reverse migration. People from urban areas going back and things like that. So basically, all the related issues directly impact in AEC. Now imagine a situation where you have a lot of people coming in the urban area. How do you provide housing for them? So then you need to do a lot of innovation, use technology, create new ways of building multiple societies very quickly. So these are the direct impact of urbanization. You need to develop, I mean, being from Nagpur, I'm sure that all of you know that length of road per day or the length of railway line per day. These are the things which basically you hear in Nagpur. So this urbanization is actually driving AEC industry to adopt technology. So what are the different technologies then the AEC is actually adopting? These are few of the recent trends in the AEC that I can mention. This is not the whole list, but this is something relevant for our today's seminar. Basically, it's real-time data and Internet of Things, that is making smart buildings. So if you have seen many of these applications, from Google to IBM Watson platform, you could have seen preventive and predictive maintenance. These are the things where you have things have internet link. That means your at home could be refrigerator to air conditioner to whatever, and those things are connected to some central hub, and then from there it goes to a processing place where different decisions are made and actions are taken. So this is basically Internet of Things. It could be a traffic management to anything. And then you have artificial intelligence. We will be talking about generative design, expert systems, and artificial neural networks today. These things are required because basic nature of civil engineering is such that you are connected with too many people, lot of subjective decisions. Suppose you want to build something, some facility, you have contractors, consultants, subcontractors, structural engineers, MEP, supply chain, a huge network is there. And these problems in civil engineering are like very subjective. Somebody wants to optimize for cost, somebody optimize for space, somebody wants better views. So these are something, the conditions or the problem area is not a clearly stated problem. So these problems are generally called ill-conditioned problem, and for that your uh, routine, like normal procedural type of programming doesn't help, and that is why adaptive learning and artificial intelligence is required. We will go into the details of this, and we'll see how this actually is applied in civil engineering. Robotics definitely for construction arms, accessing hazard, dangerous tasks, or simple example would be to lay out a grid. Uh, if it is done with the robotic arm, it is like much better and accurate. So there are different robotic applications. One of that is also in 3D printing, like you can have a robotic arm actually printing something. A wall could be actually printed instead of constructed. So these kind of applications of robotics. Digital twin, mostly I will be limited to say a BIM model, where from a 2D diagram you can develop a 3D and then take it to 4D, 5D, 6D. I will talk about what is this 4, 5, 6Ds. And these are different dimensions we can add to the BIM model, and then you definitely can have the advantage of linking it to the building management system, automation systems. It's like having a twin in your own computer, so you can do a lot of things with that building. You can simulate flow of people, simulate lift up and down, and all those kind of things. In oil and gas, this is very important because the equipments are very expensive. So for preventive and predictive maintenance, digital twin is often used there. Then there is something which is virtual reality that most of you have seen. Augmented reality, I'm not sure, but most of you have seen virtual reality. At least you have seen a walkthrough of a flat to be sold. That is nothing but virtual reality, where you just have a 3D model, AutoCAD model or any other CAD software model, and then you apply lights, material, and then render it, and you have a walkthrough. So that is basically a virtual reality, but you can make it more realistic by adding smell, adding sounds, and variety of other things to it, and make it like as real as possible. So that is virtual. And augmented is like, it's a superimposition of virtual on the actual. So if there is some site, you can put your you can use your tablet to take a picture of that, and then you superimpose your model, and that can also be done in real time. So that's about the augmented reality. Wearables basically in construction are used for construction safety. Like, if you have a particular person to be remaining in a particular area, if he goes out of that area, you can get an alarm. So this type of things, this is a simple example. There are many other applications because it is GPS based also. So basically for the construction safety. Cloud technology is definitely for the collaboration. Nowadays we have projects across continents, across countries, across cities. So for the project management, for collaboration, for working together on a project from multiple sites, and in this situation today, it is forcing people to work from home. So basically the cloud comes in very handy, and it can also be extended to offering the hardware necessary, like for in 3D rendering, you can use the cloud technology for making your renders very fast. Drones and scanning, basically it is used in civil engineering to replace our normal physical surveys. You can just fly drones with a scanner in it, and then you can get your DTM. You can go to the hazardous areas with the drone, or there are so many other applications. We'll talk about it. And another trend is basically the 3D printing, where you suppose you design something and optimize it for shape. Now you come up with a shape that is not constructible. So what you do? In that case, you need to 3D print it. Or if you have some model where you are doing a MEP design, say pipes and your drainage pipes and electrical lines, and so many things are there, AC ducts and so on. To detect the clashes, then you can just print the 3D model and actually see the workability of that model. So these are various types of technological trends. I have mentioned a few of them. These are practical. These are from the point of view that, if some of you who are listening can use this for uh, doing projects in one of these areas. This is basically to improve the employability after graduation or after courses. So that has been my point of view in selecting these technologies to talk about. But all these things are very nice, very exciting, with one drawback. And the drawback in civil engineering, that the rate of technology adoption in AEC is next only to agriculture. So this is a big challenge actually. And if you go out, you will realize that you will not see most of this in the field, because the availability of manpower is there. There is construction sector in our area is basically a job generating sector. So uh, basically it is meant to create more jobs than to automate more jobs. So there is this kind of situation where the technology adoption is very less. But with this today's situation, I feel like, we have been forced to adopt technology, and AEC will also move in this direction, and it will move very fast. So let us now look at how these different technologies have been evolving in civil engineering. So when these computers became a personal computer, we used to have basically in civil engineering something called number crunching. So whatever you have seen, like, in our time, we used to learn Fortran language or BASIC or C. Basically, it is to uh, computerize finite element analysis type of applications. Matrix analysis of frame structure, static dynamic analysis. These are the things mostly have been computerized, and they use a serial processing application, which is like, you start from something, you give an input, and the computer can do a lot of number crunching, and it gives you an output. So this is how it was for a long time. And after that, we started to get something called graphical user interface, and that used C++ object oriented programming and certain ready-made libraries, that because as coming from a domain knowledge person, having a knowledge of computer programming was not that much available with the civil engineering people. So we have a lot of libraries available that can help somebody to computerize whatever the programming they want to do. So in graphical user interface, what happened is we got this visual input and output check for our whatever the input we are doing. So for example, if you are, and most of you might be using some or the other commercially available software for, say, structural analysis. If you are using that, you must be making input in a graphical. So you can see physically in the graphical format what input you are giving to the system. And then also after the analysis is done, there's something called post-processor that presents the output in a form that visual to you, like you can see the stress diagram, the bending moment diagrams and things like that. So it's basically pre-processing and post-processing, seeing the results of your structural analysis, and those things you can actually use the graphical user interface for. And this is something a lot of people would be actually programming. So in your college also, maybe a lot of people are doing programming. This is the one area where they are doing it, or they are using a ready-made commercially available CAD software. You just start doing your programming on existing software, and then you can solve your problem with that. It also includes parallel processing, and there are different machines and workstations available. I think there is one in CDAC, something, I think Param or something is there. So those are basically using the graphical user interface for visual input and output, and then pre and post processing. And then we have this commercially available optimization algorithms. Like, suppose you are building a house and you want to do the shadow study, like from morning to evening, how the sun is impacting the design of a particular building. And then you want to optimize on something. Say you want to optimize on design, or you want to optimize for space, or say parking lots, or whatever way. Then optimization algorithms are available, and then there are a lot of commercial software development is also going on in this optimization algorithms. And then we have something called expert systems, where what you will realize is that in all the applications, you require something that that can be programmed. A logic, a flow chart is required to do the program. Whereas when you talk of advising system, or you talk of a knowledge-based system, which doesn't have a definite flow, but it depends on intuition, it depends on knowledge base, it depends on experience, it has a lot of sort of advising nature, then those things are very difficult to program. And that's where the programming or computerization in civil engineering mostly has been stagnant for a long time. So there is something called expert system. This is basically knowledge-based expert system, where you can have some sort of a knowledge base, which is in the form of a generative rules, like if then type of system you can use, and then that you can program using something, some expert system shells, or you can develop a program based on, or an expert system based on logical programming language like Prolog, Turbo Prolog, those kind of languages, or there are so many shells. We will go into more details of this, but this is basically to program something that cannot be programmed in a sequential way. And then we have this artificial neural networks. Those are useful for applications where you need intuitive design or intuitive processes, or you want to capture the knowledge. If you want to develop an expert system, you need to have an expert who will be able to give you his knowledge. But if there is nothing like that, you only have results, and you want to then develop a system based on that, then you need to have a system that learns automatically. And this adaptive learning is basically what is involved in artificial neural networks. So this is basically for predicting material behavior or learning and things like that. We will go into details of this. And then the Internet of Things is basically for making, interconnecting so many different devices, and then processing that input to make a meaningful decision. Something like, you can get input from SCADA system and then process that and make, I will show you one example of this Internet of Things also. AR, VR, we just talked about it a little bit. It's for visualization, design visualization. It can also be used for assembly instruction. Suppose you are importing a huge machine or some system from abroad and you don't know how to assemble it. At that time, you can use this VR, and it can also be used for training and other purposes. Generative design is a recent development where you can use it for creating thousands of design alternatives with the given input conditions, and then you can select based on whichever parameters you want to optimize. It requires 3D printing, because the shapes that the generative design will create will be so difficult to manufacture that better to print it in 3D. So those things are there. And then we have this BIM, which is not the very latest, but the most popular. I mean, if you go out in the market, mostly we'll be talking about BIM up to 3D or 4D. And then maybe if you are in a metro or some other city, you will be talking about BIM and facility management integration. Because once you have a 3D model, you can actually integrate that with the facility management and have a very good management tool for, because 80% of the building life is in the management, not in construction. Construction is only the 20% of the building part, building life cycle. So these are the different applications in computing. And let us go into two areas which we want to look at. That is the building of an expert system for civil engineering. Now, when we talk of a knowledge-based expert system, first of all, what are the application areas for it? First is the area where any area that really requires intuition, or it requires rules of thumb, it requires heuristic knowledge, it requires something that you cannot definitely express as the algorithm. So for example, if you look at a particular building, maybe you will be able to say who is the designer. that means, like, that particular designer has a imprint of his design style on that particular design. So this expertise you can actually catch hold of by doing something called a knowledge acquisition process, and then use that knowledge to create some rules and then develop a system. So this is something which is a system which is based on the particular expert's knowledge. I will give a simple example of how this works. If you see a open electric wire, most probably none of you will go and touch it, because there is a knowledge in your brain that if you touch a wire which is open, it might have a electric current in it and you might get a shock. Whereas a small child may just go and grab that wire. He might find the color attractive and he will go and grab it, because there is no knowledge that it might give him a shock. So basically your action is as much intelligent as much you have the knowledge. So basically that is what this knowledge based expert system is. I can, like, in a layman's language, I can explain that for structural design, which is like initial design, any design is a good design, because somebody wants to optimize for, say, depth of a beam, somebody wants to optimize the cost of a design, somebody wants to optimize for amount of steel used, or whatever the parameter. But different designs are there and all of them are good as long as they don't fall down. So basically it is a expert's view then, and so you can use an expert system for coming up with a design as that particular expert will design it. So this system will give an output depending on who is the expert and what is the level of capturing the knowledge from that expert. You can use this for synthesis of different alternatives. You can use it for bidding estimation. So suppose you want to bid for a particular project, then you can have a rough idea about how much it will cost based on the previous such designs done and previous costings. I can give one example, like maybe there you have something called ready reckoner or something rate. Suppose you want to buy a house or a flat, or you want to sell it, then there is general market rate in that region. So that is basically a knowledge base, and you compare whatever you are doing with that particular knowledge base or that particular database. So that's how I can explain this as a tool where you can use the expert system for estimation. I mean, in today's scenario, if it is for advising purpose, it could be like, if you have a fever and you have traveled abroad, then maybe you should get a COVID test. So this is kind of application where an expert can be used, or you can use it to fill in for an expert. So this is what I mean, like, nowadays you will see a lot of application like this on internet. Like, if you want to have some decision, they will ask you certain questions, you answer those questions, and then some result will come out. What it is doing basically is a knowledge-based system, and it is using if-then type of rules. So this is the basic architecture of a expert system. Suppose you want to use an expert system for designing a single span beam. Now, a single span beam, I'm taking this example because I will use the same one to explain the development of artificial neural network as well. So these are the different parameters or different parts of the architecture. So you have an expert. This expert he knows how to design, or he knows, or he does in a particular way. And then there is something called knowledge acquisition process, where you can extract the knowledge of this expert in the form of if-then rules. So you ask him a lot of questions, you do his interview, you take the design examples done by this expert, and then you create a database where if you create a set of rules, if and then what happens. So if condition A is met and condition B is met, then it will be basically particular result. So this kind of results you can you can acquire from an expert, create a knowledge base. Then there is something called inference engine. These are like very basic architectures I'm showing, because I don't want to go into very detailed process. And you can use ready-made shells actually for this. Nowadays it's all available. You just need to have your knowledge base, and you can have an inference engine and user interface ready-made. You can use it. And the advantage is that once the output is obtained from this system, you can get the explanation, because it will explain how the system has arrived at a particular decision, because it has used this if-then rules. So this is how basically the architecture of an expert system works, knowledge-based expert system. And you can make rules over here about design, like, if the span is so much, and so much is the limitation on cost, and then this is the design, or this much is your cost per meter require or limitation, and this is the limitation on steel, then this type of width and depth is required. So these kind of rules you can put in and create a design alternatives, basically based on the knowledge of that expert. This is how the expert system is developed, and depends on what is your problem and what kind of expert you have, and how much proficient you are in extracting that knowledge from the expert. So the parts involved in development of this knowledge-based expert system is knowledge acquisition process, then selection of an inference engine, or this is an area where you can start developing one of your own. So you get to do some programming also, and then you can have your own engine for knowledge-based system. And then you develop pre and post expert, like, how are you going to give the input? Are you going to give it as a symbol? Are you going to give it as numbers? Are you going to give, what kind of input you are going to design for your system, and how you are going to interpret the output of the system? So these are the three different stages in development of knowledge-based expert system. And the whole thing basically remains around the knowledge acquisition process. The limitations of these systems are basically, it is only as good as the knowledge base. It cannot handle any new task. It can handle only a particular task. Then there is no underlying process explanation possible. It only tells because of this it has done that result, but why it will not explain that. And there is no generalization of the knowledge. Like, it doesn't use it for any other new area or any other thing that is like, apart from the problem for which it has been trained, for which knowledge has been extracted from expert. It remains limited to that, and it doesn't learn on its own anything. So it lacks a learning capability. So basically it is a extrapolation of the expert's knowledge. So it can't learn anything on its own. And since these shells are based on the if-then type of rules, heuristic rules, they can't be incorporating any number crunching. So you can't develop a system in the same system, like you do a matrix analysis and also use the interpreter. That is not possible. You need to then link 2-3 different systems to one another. A new architecture has to be developed for that, and then only you can use it. I'm talking about design particularly, in structural design also. But if you are using it for, say, geotechnical area, for environmental, then these things can do much better job actually. So this is in short about the knowledge-based expert system. And using the same example of a single span beam, let us now look at the artificial neural networks. And if you look at difference between the expert system and artificial neural network, expert system doesn't capture the deep knowledge. Now, what I mean by deep knowledge is that you just produce some examples and the system automatically takes out the knowledge which is like deep in nature. That means it's intuitive in nature. A neural network, on the other hand, it has the capacity to capture the unexplained logic, and it can also generalize the knowledge. That means, you specifically train it for many different examples, and the neural network will generalize the knowledge in the forms of, okay, I will explain that when we see the structure of a neural network, then I can explain like where it generalizes it. then it can also be used for a new set of parameters, because it is actually generalizing and it is self-learning, self-organizing. So it can be used for new set of parameters, and it can also be used for optimization, simulation, and just knowledge representation. You can store the knowledge in it. You can use it for simulating different situations, which are not possible using procedural programming or graphical programming or even in our expert systems. And it does capture the human intuition in the form of different neural properties. In the computing in civil engineering, we have references for use of neural networks since 1990. So if you really want to do a literature study, you can go up to 1990 for finding like different initial efforts that researchers have put in developing neural networks for civil engineering. And basically, any ill-conditioned application is suitable for this type of artificial neural networks. So if you have a situation where you can't really define your problem, that is the area where neural networks will be best suited for civil engineering applications. Now, I'm going to look at designing a neural network, and then the training of the network, designing of the network, and testing and use of the neural network using a simple example of a single span beam, which looks like a simple example. And I have selected it because there is an optimization algorithm available just to create a lot of examples. If you look at a preliminary design of a structure, it requires a lot of knowledge, rules of thumb, intuition, past experience, different constraint of space, of cost, constructability, different situations of a structure, whether it is composite structure, different materials. So many different parameters are there. So to come up with a preliminary design for a structural problem, artificial neural network is very much suited. So let us see how we can develop this and what are the different parts of this neural network system. Now, this is a biological neuron and this is a simulated neuron. It's a mathematical model. So basically, if you see the natural or biological neuron, you will see that this basically functions. There are billions of them in the brain, and how they function is like they collect the input from other neurons through a connection point called synaptic points, and from there these dendrites take that input into the cell. And then each neuron has a threshold value, and it sums up all the input. Like, here if you see, all these are the inputs from input to this particular neuron, and these are the weightages of those connections. So there is this dendrite is connected to another neuron through a connection point called synaptic point, and the output is going out from axon. So basically what you see in mathematical model is that these are all x1, x2, x3 are the input, and these are the weightages of those connection to this particular neuron. It sums it up, and then there is something which is a function of this neuron, the threshold of this neuron, and if that is triggered, then it sends the output to other neurons. So I mean, this is the maximum mathematical slide I have, so don't get afraid. I'm not going to go into the neural network design mathematical details and all here. Just to explain that, this summation is processed through some function. So I'm mentioning three functions here, which is like a hard limiter. So it's like plus minus. Those who have some electrical background, they know, like, and or and those type of functions. Threshold logic is like, it goes up to a particular threshold and then it will fire, and or the sigmoidal logic. So these are the three different functions that a neuron is using, and then based on the input and whether the function is triggering the output, one of this function you can choose for your network, and then it will send the output to other neurons. So it will calculate all the sum of the connections coming to it. This total is then compared with the threshold, and if the threshold is triggered, output will be sent to other neurons. So this is the very basic form the artificial neuron is going to work. So then how do we design it, and what are the different types of networks? So I have two different type of networks here. One is called the Hopfield, which is basically, this one stores mostly the patterns and the example patterns with the examples which you use to train a network. Those are used in this and they are stored basically in this. And then similar pattern only it will process. A new pattern it won't really process. Whereas this is a feed forward network where you can see, like, this is the input layer, these are hidden layers, and then this is an output layer. Now what happens is you have to design a network for your problem. That means you have to select the input layer, you have to select how many neurons you are going to use for this input, and how many different layers you will use in the hidden layer area. Here there are two hidden layers. You could have many, you could have less. It could, if your problem is simple, it doesn't require deep learning, you can go with only one. And then you have to design the output layer. Now this is a network where the threshold of these neurons will be adjusted automatically during the learning process, and the weight also of these connections will be adjusted automatically by the algorithm. There are different learning algorithms. One we are going to use in our example is called backward integration. So that algorithm we will use, and I will show you how it is trained, and then how the weights are automatically adjusted. And then the knowledge is basically stored in the form of the threshold of this neuron and the weights of these connections. This is where the knowledge is stored. So this is totally different from a computer program where you process number crunching type of data in normal systems. So these are the two different types of networks that we are going to look at. Out of this, for our example, this is more suitable because here we are going to give the input for our beam problem. That is a span of the beam, dead load, live load, and types of steel and concrete, and then we will get the output in terms of width and depth and steel and cost and all those things. So this is basically a feed forward neural network. It has two hidden layers, one input and one output layer. All these things are connected, and weights will be adjusted during the forward and backward passing. We'll go through this now, how we develop that. So basically the formula that we are using for generating the sets of good design is this. I'm not going to explain what this is basically a cost function for to minimize for an optimized design of a beam. So there are different parameters of this beam, and then there are different A1 to A6 are different constants, which I'm not going into the detail of this. Basically, I just want to explain that some algorithm we have used to have different constraints. These are all different constraints on the cost function, and accordingly, the training examples have been developed. So basically, for computerization of the initial design process, then since this is basically a guesswork and experience of designer, and knowledge about the constraints are only with the designer, and also he knows how to, what kind of output will be having a constructability. So this is what we are going to train the network for, and it will then predict the output for a new problem, which we will then compare with the output of an expert. So now let us go through configuration of the neural network. Now, as I mentioned, these are the input layers. So you can see here, you have a span, dead live load, dead load. These are two concrete mix, and these are the three steel types. So basically it is 8 nodes, 1 node each for span, dead load, live load, 3 nodes for grades of steel, and 2 nodes of grades of the concrete. Now, this could be any other input for any other problem. So if you are not from structures, you are from some other discipline, you want to develop it for some other thing, you can have your own parameters here. These two sets, two layers, I will come to how you design these two hidden layers. And then the output is in the form of steel area, depth, width, etc. So these are the output parameters, and these are the input parameters. So this is what the first step in developing a neural network. Then you have to normalize this, because this whole thing is functioning in 0 to 1 level. So For example, if you have two concrete grades, then you can use 1 and 0 as input for two. If you have three, you use different combinations. And if now the load cannot be between 0 to 1, so you have to normalize it. Means divide it by the maximum one. So the maximum one becomes 1, and then you have the range in between. So that's what you do for normalization of input. Similarly, you normalize the output. So when you get the new output, you convert it back into the language that is understood. So then another main thing is selection of training. Right now, we have selected a back propagation algorithm. There are different training algorithms. You can find it in literature study. There are, and these are like, well established algorithms for different types of network. You can use any of them. For the training of a feed-forward network, we have selected here the backpropagation algorithm. That means it is going to distribute the error that comes when you first time train the network back into the neural network with weights and adjustment of thresholds. And selection of layers. So whether you go for one layer, two layer, this is a trial and error way. There is no particular guideline for it. It comes with experience. You will over the time develop some experience where you can know that this type of problem, what is the complexity of the learning required, and accordingly you can decide. But this is basically when I have developed this network, I had to do a lot of trial and error because there was no literature available and there was no guideline available. So basically started with single layer, then tried to make it learn. It didn't learn. It had a lot of errors. It did not have sufficient tolerance, fault tolerance. Fault tolerance means suppose few of these nodes are damaged, then still your network should work. So in that case, you need to basically have a fault tolerant, means you need to have more layers. So this is with the trial and error. We have done two different layers with 30 nodes each in each layer. Now you could have a different configuration and still have the similar results, or you can go for a deeper network and quickly have a better result. It depends on how you want to do it and whether you can you intend to have a physical model of it. Like once this network is developed, you can develop a VLSI design type physical structure for simulating the network, and then you can have a physical network also. So this is the training set. Then, like this is the input parameters and these are the output parameters. So these are examples for the training purpose. So these examples will be given as input, and then we will see how the actual development process happens. So first we normalize the input. Second is we have to develop a simulator. So here is another opportunity for getting into software development and developing your own simulator. Like I have developed my own simulator that was in C++, and it was long back. But now you have variety of new tools and software development support available. So you can actually develop your own network with graphical input, output, all kinds of windows and other functions to it. And that would be a good simulator. In fact, what you could do is, like if you have a team of students or people, you can use it as a separate projects for each one of them. So one can develop a simulator, somebody can develop other things. So different parts can be developed and a total project can be divided like that. Because this development of simulator is a big development thing. It takes normally 8 to 9 months to develop this simulator, because you need to test it, develop it, and there's a lot of process in that. Then once you have the simulator, you have this input, the sample output. What you do is basically you initiate the network with random values. So to start with, the network has no knowledge. So you just provide the input pattern to it and it will produce whatever output it can. So this is with the randomly initiated weights and thresholds. Once you have those output, then you compare that output, which is given by a randomly initiated network, and then you back propagate the error into the weights and thresholds of each connection and the neuron. So this is how the actual training works. Now here you can see that in the this is basically where we want to learn, and this is for the depth of the beam. Then this is for the width, and this is the steel area. You can see here that for the depth it has been trained very well, because the important criteria in this design example what we have taken, we consider depth. You can choose any parameter actually, there is no binding on it, but depth of a beam was supposed to be a parameter to look for, just because this is all study purpose, right? So you can see here the depth has been trained much better, and these are all number of cycles in thousands. So the first, you have all kinds of error in the output, then you back propagate error. After 1000 2000 cycles, they are coming nearer to what you desire, or what is the actual output of the expert or the optimizer. And then after 5000, it is looking like, okay, we can use this, learning is complete now. Now this learning, you can decide what is your tolerance level and go continue to train the network up to the level of your satisfaction. In this case, after 5000, the network has automatically adjusted the weights between different connections of the, I mean, these connections, these weights have been adjusted for different connections, as well as the threshold of each neuron has been finalized. So after 5000 times this example set is presented to the network seems to have learned automatically that when a particular set of input is presented, what is the expected output, and that knowledge is now in the network. So this is how basically the training process works. And then what we have observed is the threshold values change very rapidly as the network converges. So that means the basic knowledge of the network is in the thresholds of the neuron, not so much in the weightages of the connections. But yes, weightage is also important, and that also will, I'll show you in the next few figures that why that is important. Because if one node gets damaged, then suppose you have physically prepared, made this network into an electric diagram or an electric circuit, then if there is one node damaged, then your output will be affected. So that we will see, like, how the node damage impacts the performance of the network. So basically it is the network is then trained, knowledge is there in the system, and after the training it is then tested for the new problem, and then the knowledge basically is in the node threshold of the nodes. One more thing about the training is that when you present a training example sequentially, these are different types of training patterns I have presented, and this is the output. Where here you can see that if the example is each example is sequentially presented and the whole set is presented like that, how the network learns after X number of cycles. Here it is after 600 cycles. Here you can see, like, it is whole set is presented, and then each whole set is presented, but each example is presented 10 times. So there are different ways of training, and these things will come to you after you do different type of experimentation. But this is now a finding which could be used, and you can reduce your training time for the network. It's just for the information purpose. Then here is the example of evaluation of this network. So after the training, then the network is presented with new examples for which it has not been trained. And then you check the output of the network. So to verify, in this particular example, a 5% tolerance limit was accepted as okay, because this is an initial design. Anyway, this has to be further optimized. So for initial design to start with, 5% tolerance was accepted. So this is here in the table, there are like different new examples, and here you can see what is the result we wanted, and what is in the bracket you can see the deviation. So this is basically the delta that you can decide whether you want to accept this or you want to continue training the network. As you train more, it will become more and more convergent, and this difference will keep reducing. And you have to then decide which are the parameters you want to monitor most, and then if those parameters are within limit, you can tolerate, or you can have a higher tolerance for the other input or output parameters as per your design or your problem definition. Then there's also possibility that you can develop another configuration with different desired result and different tolerance limits. All these things are basically part of trial and error. You need to do that, and then when you develop another configuration of the network, train it in a different way, you can get different desired results or different tolerance limit with different type of different configuration of the network. And this is like, applications, any applications you can then give it. When this particular formula, we use an optimization formula, but if it is not there, you can just use input and output examples and the network will still learn this. Then shortly, I think I'm almost running out of time, so I will just very quickly go through certain things. Fault tolerance, this is the fault tolerance study. Like, you damage node purposely. So one node is damaged, second node is damaged, and then you can see, like, as the number of nodes are damaged, the performance deteriorates. And you can also see, like, which parameter is most affected when you at how many number of nodes, and all those studies you can do basically. This is a massively parallel processing system. So some nodes, even if they are damaged, it's okay. It's still, the network still performs, but you need to do study of your own fault tolerance for the network as to how many nodes it can tolerate to damage. This is the different parameters. Like this one is for the width, this one is for the depth, and you can see, like, since the network is trained for a particular parameter, that parameter will not be damaged much. So this is how basically you develop a neural network, you configure it, you train, you test, and then you can use this. As this is a possibility to use in a hybrid environment. So here there is one more architecture I have shown. You can use it for initial design, then use your procedural language for analysis, and then for detailed design, again, you can use expert system or neural network and things like that. One important thing is, like, you can do a reverse study as to which parameter is important for your result. So you can do that study, like, reverse study is also possible, because now the network has learned how to predict output. You can use that for studying, like, which parameter is more important. If you have a if you don't have a particular input, then how the output will be affected, and those studies you can do. The shell for the neural network you can develop in any programming language. So that means you can integrate procedural routines like matrix analysis of frame structures or something like that you can include, but then it has to be a separate module, and you can use this to append the neural network, or before or after you can use it. And with cloud and parallel processing, neural network, generative design, you can come up with variety of these architectures, and you can produce a lot of new designs. So basically, this is in short. I can explain the application of neural network. So what we have seen is, like, expert system, limitations of that, and then how much you can go further in programming for civil engineering, different applications with neural networks. Now, before I close, let me just touch shortly about a few things. I will go really quickly over these things, almost out of time. This is an example of a generative design. So basically what it is like, it has an automated optimization algorithm that can create lot means thousands of feasible design options, and then you can select one of that. So this is the constraint could be space, could be cost, material, performance requirement, manufacturing, and so on. So it's basically a system which is little bit extension of self-learning, and the more it is used, the more it learns automatically. So it generates more and more design, and it also incorporates the optimization parameters, provides a lot of examples, and then based on here you can see the parking space are being optimized in this animation what you are seeing on the screen. So these are the different applications of generative design. This video, I might want to skip it because we don't have time. The research by Marcos, this is an example of generative design. This is a PhD thesis actually, not yet completed. This is being done in a university in Canada, where they are using a mix of 3D printing, automation, and generative design. So basically, if you see, there are different types of uh, structural designs possible. All these are coming from generative design. These are the parameters where optimization is happening. And then the actual construction is also is there. I don't have time to show all that to you right now. But this is one of the PhD thesis, and there is a startup company also which Marcos has started based on this research. So it's basically to design very optimally and use optimum material or whatever the parameter you want to optimize. These are certain examples, like Autodesk has developed this landing rover for interplanetary lander. You can see it here. This is for optimizing the weight. They have reduced 35% weight. This is another example of a chair which is designed using generative design. If you go on the web, you will find all this, a lot of information is available. Lastly, Internet of Things. So I will just explain what basically it is doing in the civil engineering. So it is basically a lot of input coming from different equipments, power, people, environment, and so on. And then using analysis and action center, where you can use rule base, or you can use automated work orders, FM integration, facility management integration, and then automated actions are triggered where you have a work order sent to some repair company and things like that. So this is basically what it is. These are different applications for the IoT in civil engineering. Basically, for suppose it's a house, then if there is a sunlight coming in from somewhere, curtains can be automatically managed, and for traffic management or equipment and things like that. So these are different Internet of Things applications. This video actually shows, this is a 2-minute video, which again I would like to skip because we are out of time. And then the AR VR applications. This, I think, in the initial introduction, I talked a little bit about it. So this is basically to have an immersive experience with environmental effects, sounds, smell, light, music, everything possible, and then you can feel like you are in a particular environment in a virtual way. And nowadays, with a lot of people staying at home, it can be used for selling properties and designing and things like that. So basically, this is in short what the different technologies are useful in civil engineering. BIM, yeah, just I would briefly mention what is this 3D. 3D, everybody knows it's a 3D model. 4D is when you include construction sequencing. For example, where to place a crane when you are building your building, so to check the municipality permission and all. So that is how this 5D cost and 6D, so including maintenance and all. These are the extension of the BIM. And I think the scanning and drone, those things I have mentioned. So I won't go into that. And yes, 3D printing also, a lot of information you can find it on the web. So this is in short, I would like to conclude with on my topic today. So I again thank you all for joining me and giving me this opportunity to talk to you. It's been a pleasure. And I would like to hand it over back to Vivek.